Hey guys, welcome to the introduction of logistic regression. Today, we're going to talk about what logistic regression is and how it works on classification tasks. Firstly, let's take a look at what logistic regression is. Logistic regression is a predictive algorithm that uses independent variable to predict dependent variables, just like linear regression, but here our target column must be categorical. Here's an example of linear regression where the target column is numerical. And here's an example of logistic regression where the independent variable is numerical or categorical, whereas the target column must be categorical. Now let's understand why we should use logistic regression in the first place. Here, logistic regression measures the relationship between an independent variable and dependent categorical variable, bases its probability scores out of it. Example, using income to identify the gender of an individual. Logistic regression is used in football matches as well. Suppose you want to predict if a player will score a penalty or not. Here, the outcomes are, and the indicators that would determine the outcome are. Now let's look at what the problem with using linear regression on categorical data might be. Consider this scenario. We have a dataset of students' marks and their corresponding results. On the x-axis we have marks, on the y-axis we have the probability of passing. Now let's pick a threshold of 0.5 where absolute 1 means pass and absolute 0 means fail. Now suppose we found the best fit line and we pass it through our data. Considering our threshold of 0.5, our cutoff comes out to be 50 marks. Anything below that would be considered failure. Anything above that will be considered pass. All well and good. Now let's say we got a new point over here. Then our best fit line shifts and our new cutoff will come out to be 55 marks. As you can see, these 2 points, which were previously passed, are now in the fail category, just because of an outlier point. Well, how does logistic regression solve this problem? Logistic regression uses an S-shaped squiggly line to fit the data. Just like that, it fits the data, and now our cutoff comes out to be 48 marks. Here we see that the S-shaped squiggly line has fit the data and classified all the data points almost perfectly. Now the question arises, how do we get the squiggly line? Before that, let's first see what the squiggly line indicates. This point shows a very little chance for low performers. This point shows a 50% chance for average performers. And this point shows a 100% chance for high performers. Now let's see where the S-shaped squiggly line came from. Something called a sigmoid function to transform linear regression straight line into logistic regression S-shaped squiggle. The linear regression can also be represented as log of odds in logistic regression. Let's discuss what log of odds is and why we need it. In linear regression, the value on y-axis can be any numerical value. However, in logistic regression, the probability values on y-axis are restricted between 0 and 1. Therefore, to overcome such restriction, we transform probability of passing into log odds of passing. Log odds of passing will range between negative infinity and positive infinity so that it acts just like linear regression. Now let's talk about how log of odds line is formed. We take each threshold from probability of passing, plug it into a logit function and get new threshold for log odds of passing. We use logit function to convert probabilities of passing into log odds of passing. The logit function is log of p upon 1 minus p, where p indicates the probability of passing. With that said, let's take 0 as our threshold from probability of passing, plug it into the logit function, and we get negative infinity in log of odds of passing. Then we take 1 as our threshold from probability of passing, plug it into the logit function, and get positive infinity in log odds of passing. We do the same when threshold is 0.5, plug it into the logit function, and we get 0 as our new x-axis. Take old threshold of 0.75, plug it into the logit function, and we get 1 as our new threshold. Old threshold of 0.88 to get new threshold of 2. We use old threshold of 0.95 to get new threshold of 3. Then we repeat the same for rest of the thresholds. Now that we know how log of odds line is formed, we will again come back to this in a bit. Finally, let's look at how logistic regression finds its best fit line. Unlike linear regression, logistic regression can't use residuals to find its best fit line. Instead, logistic regression uses something called as maximum likelihood to find its best fit curve. Firstly, let's pass a line through our log odds of passing. Then we project each point from infinity space to our line. Now that we have the log odds of passing line, we will transform them back to the squiggle using our sigmoid function. For instance, here we take negative 2.1, plug them into the sigmoid function, and we get probability of passing equal to 0.12. Then again we take negative 1.7, plug them into the sigmoid function, and we get probability of passing equal to 0.15. And we do the same for rest of them. First, calculate the likelihood of observing each non-passing student. Then calculate the likelihood of observing each passing student. We will calculate the log likelihood for each observation and sum them all up. We get negative 1.672 as our log likelihood for this line. Then we rotate the line and calculate log likelihood again. We project points from infinity space onto our new line. Plug the projected points into a sigmoid function to convert log odds of passing into probability of passing. Then we take log likelihood of each non-passing and passing student and sum them all up. We get negative 3.146 as our log likelihood for this line, which is worse fit than what we had before. And we just keep rotating the log odds line and keep projecting the data onto it, and then transforming them into probabilities and calculating log likelihood. And we keep repeating the process until we find best fit curve with maximum likelihood. In conclusion, here's a quick recap. In today's video, we have learned what is logistic regression. We have taken a real-life example of logistic regression, whether a player will score a penalty or miss it. We have addressed the problem that linear regression faces in classification tasks and how logistic regression solves it. We have understood the working of logistic regression. We have computed maximum likelihood to help logistic regression find the best fit line.